Ladies and gentlemen, please welcome Mr. Dan Braley.
Thank you, everybody. So, it is my pleasure to moderate today's discussion, and well, I'll start out by introducing the panelists that we have here. Directly to my left, we have Keth Housel. Keth has 14 years in Composites, 6 years at Hitco in R&D. Later worked for Swift Engineering, Aerofide, Carburis, and is currently the Technical Director of Composite Solutions Corporation. He's a proud Iowa State graduate. Please welcome Keth Housel. Next down the line, we have Darren Boyce. He has 16 years in the composites industry in manufacturing, RTM, pre-preg, open molding, and is the inventor of the heated tooling system for the Advanced Composites group. He's a proud ASU grad. Please welcome Darren Boyce.
Right there.
Woo! Alan Hyken. He has 15 years at Northrop in positions of increasing responsibility. Started out as a lowly Mantech engineer, and later had roles as IPT leads for the YF-23, F-18, and F-35 programs. After these roles, he moved to Rubbercraft to become the Vice President of Engineering and Technology. He's also a proud Mizzou grad. Please welcome Alan Hyken.
All right, Alan.
Keith Young graduated with a PhD in mechanical engineering from Washington University in St. Louis. He has 18 years in advanced manufacturing technologies, living the deployment of titanium and composites on the 787 for the past 10 years. Keith is currently the Composites Director for Boeing Research and Technology in St. Louis, or, well, in all sites. Please welcome Keith Young.
Good morning.
So, we'll start this out by asking I'll start out by asking questions down the line here, and after each one of you guys has spoken, we'll give an opportunity for the panel to kind of rebut or talk a little bit more, and look forward to a good discussion here. So, with that said, Keth, as those of us in the composites industry, or composites and aerospace industry have witnessed, out-of-autoclave technologies have become increasingly more popular. Based on your experience in regards to manufacturing technologies of advanced composites, can you elaborate on what you are seeing in this area and what you believe the future will bring?
Definitely. All right, am I on? All right. Okay, everybody. How's it going? All right. So, it's a good question. So, if you didn't quite understand that question, he was asking, basically, okay, where's out-of-autoclave composites at today? You know, kind of from my viewpoint on the manufacturing side, and where is it going to be going? So, if you know me or don't know me, I spent my whole career on a Tier 2 level. So, never worked for an OEM, don't plan to. You know, I've always been kind of boots on the ground type of guy, hands-on. So, I feel I have a very good perspective because everything I do every day deals with cost. So maybe a lot of you guys, you know, your places, okay, I can't always afford to get the best of everything. I kind of got to shoot from the hip sometimes. So first, let's talk about where the industry is and maybe some of the challenges, and then we'll kind of go from there. So traditionally, what you see based on history are autoclave systems. You know, we're looking at various types of pre-pregs that we put in an autoclave to cure them. You know, it has a time inside there where we have to wait. So, you know, that's a cycle time issue. So we have cycle time issues, cost. Obviously, you know, you're putting more manpower and putting more cost and labor. Equipment. I just bought $1 million autoclave because we were expanding, but you have to, right? Okay. And what that also creates is it limits your supply base. So you have a high barrier of entry. So say if, you know, some guys have a good idea and they want to start a company, you got to come up with $10 million in order to get your foot in the door. So, there's challenges there. It's not necessarily bad for all of us, but for some growth, it could hinder. And why is that? Well, if we look back over the last 20, 30 years, we have materials that have been designed and developed in the 70s, 80s. They got their A and B based allowables. They've been proven to the FAA to fly over and over again. That's good. That's perfect. But there's also a point where we need to continue on to enhance technology in order to reduce costs. So I think that's one of the root causes. You never have time. In an ideal world, sure, these great ideas, we want to use them, but we need to get this plane to market because we need to make money. Okay, so that's kind of the baseline. So let's kind of expand on that. So out of autoclave. So it is being used today. There's a lot. There's a lot out there. There's a lot that's flying on aircraft. Probably the most recognizable would be Cytec's SciCom 5320-1. I'm pretty sure all of you have heard of that or come across it. Dan and I talked about it. I know Boeing uses it. Northrop uses it. They've even done a primary structure on some Bombardiers using it, a C-Series.
Yep.
So, it's out there. It's great. My experience is I've used it personally, and there's even others. Torre. If you all probably heard of the Agate system, it's kind of its street name. I've used that on a lot of aftermarket type of applications for winglets, fairings. That's kind of my go-to for design because it's a public free base for A and B based allowables. So if you got an idea and you want to design it, the FAA recognizes that out of autoclave product. And then another one, try to get more people involved, the Hexcel L501 is a fiberglass out of autoclave system that we use daily at my facility, creating aftermarket fairings. So them are just some examples that they are being used, FAA recognized. You can cure them in just a standing oven. You don't need an autoclave. And you get good mechanicals, and the cost is, a little bit less than autoclave material. So that's kind of the line there. So that's kind of a step down from your traditional. So let's go a little further. Okay, so how do we go beyond that? Okay, so the challenge with the ones that are out there, you still have your cure times. You're still looking at 4 hours, 6 hours. So you reduce your capital expenditure. You've reduced your cycle time, your cost a little bit. But how can we go beyond that? So if you look at the high rate, so what if you need to build 20,000 parts a year? When you look at that, could you cycle that through that type of traditional sense? Maybe, maybe not. So looking forward, I think we need to step into the realms where there's a lot of debate. Thermoplastics, for one. Everybody's like, it costs a lot, It does cost a lot, but it's coming down. That's one little carrot. RTM. So that's a big one there. And we're gonna peel into that a little bit more. What are the challenges there? Well, okay, you can buy carbon pretty cheap. You can get resin pretty cheap. How do you put them together? If you don't get that right fiber to resin ratio, that's a problem. You get too much resin in there, it's not very strong. Well, there's been a lot of advancements with using preform calls or closed systems to where they can really press it to get the higher fiber volume, which is now it changes the game, So that's some stuff in the future that's coming along, and then there's obviously a lot of there's some other proprietary IP systems which still have costs associated with them. If you've heard of the Quick Step system, which I know SMB has talked about in the past, and then even Globe in Tacoma working on their rapid clave. So there are some other out of autoclave things. So there's a lot going on in the industry. But the real question comes down to this. So we talked about cost, we talked about the equipment, but what's going to drive the change? So if we go back to the root issue is the reason we're not using that is because they're not proven. The FAA only backs stuff that they know is going to be safe. So this is my 2 cents on it. I'm just going to add my finishing line. It's more, I see a change in the future where the barriers of entry are becoming more feasible to overcome due to process improvements, material technologies, and cost down initiatives. So, if we're trying to reduce cost every year, it's very important that we look into these. However, I think the root thing is a change at the design level. So if the OEM level, I know is working that, and as they continue to push that design level, it's a faster way to turn a corner in the industry. Design for cost and producibility. That should be the mentality. If you're designing for cost and producibility, you're going to hit the best solution for the product at hand. Thanks.
Thank you. You've also done quite a bit of work within heated tooling. And can you discuss some of the roadblocks that are currently present with heated tooling and how you can overcome those hurdles?
Definitely. So I'm just going to tell a quick story, and then I'm going to lean on my panel, Conrad here, Darren, because we actually have a real story that kind of ties into this. So a few years ago, I was working on a project. Actually, I see an engineer out here, Alex. He used to work for me. It was a similar program we worked on, and we were trying to solve a high-rate solution. A customer came to us and said, hey, we build a lot of these parts. We want to find a better way to build them because right now we have 30 or 40 tools, and we lay it up with pre-preg every day, and we put it in an oven or an autoclave every day and cure it and pull it out every day. And I have 30 people that do it every single day. If you lay that out, it's not very cost-effective, I was like, okay. We've been dabbling in some RTM solutions because it's, non-critical structure type system. So we started doing tests. We're like, hey, we could actually make this part using dry carbon, some fast cure epoxy resin systems, cures in 4 to 6 minutes. Okay, so we came up with a plan. We got a well-recognized tooling company in aerospace to quote us a high-rate heated tool that costs probably upwards of $100,000, which is about right. It's not overpriced. Mm-hmm. And so we put together a business case, looked at how we could do it. We needed 4 of them or something. Did an ROI, sent to the customer, compared it apples to apples, and it was about the same price as buying 30 to 40 tools. But they were like, well, it's not. No one's really doing this, so we're not going to do it. We're afraid of it. We're afraid because it's something new.
Right.
So that went away. So a week later, Darren shows up at my facility, and I kind of told him my story, and he's like, oh, well, what if the tool didn't cost that much? I'm like, oh. So we started talking about technology he's been working with using carbon nanotube technologies in heating through composite tools, which obviously, if you're building a composite tool, you can use a master over and over to recreate tools at a lower cost. So I'm actually going to kick it to Darren because he knows vastly more than I do on this topic. Darren.
Okay, ready? Okay, am I on? We on? Okay. Well, to add on to what Kes said, there's a number of things in heated tooling. Obviously, when he discussed the autoclave, there's some large costs in purchasing just a tool to cure composites. So one of the things that people look at when they build a part or they cost it out is the cost that they have to pay to cure it, and put it into an autoclave. And naturally, you want to try to knock those costs down. So one of the ways to do that is to try to take it out of the autoclave and cure it on the spot. Now, there's a number of things that you can do in between there. You got ovens, you got out of autoclave, et cetera. But heated tooling actually comes with a number of benefits. And I'm not trying to make a sales point here, but this heated tooling can actually do a number of things. It can be done in composites, it can be done on metal. So you can heat a tool on a shop floor to either cure out of autoclave laminates. You can use it to heat up to do layups. So unlike an oven, when you have to run it through a cycle, you can put a tool on the shop floor, heat it up so you can lay down BMI tapes, you can lay down pre-pregs, you get the tack that you need. There's a lot of facilities that are in cold environments. They have a hard time heating up metal tools or even composite tools. But really, a number of the costs that are saved by heated tooling specific to out of autoclave is to take the tool out of the autoclave, out of the queue, off to place it in one spot on the shop floor, and to heat up and cure a part and cool it and demold it, and then do it again in the same spot and do it again in the same spot, and not have to move that mold. You can almost permanently mount it. You can heat it up gently to apply the pre-pregs, bag it, cure it, and do all that kind of stuff, and not have to go through the autoclave cycles. Because autoclaves are, some of them are extremely large. We've worked with this and some that are 22 by 60 feet. They're very large and
Expensive.
And when they take certain cure cycles, you can only include products that have that same cycle. So you end up with a very high cost trying to cure a laminate that sometimes isn't really justified. So you find ways to, or you want to find ways to do it inexpensively, to produce some of the lesser expensive materials on the tool, on the shop floor, without all the expenses of the ovens. Now there's also, that I would consider that probably the holy grail of heated tooling. There's also the issue of heating up a tool consistently, the temperature gradient's consistent inside an autoclave. So there are some tools that the way they stand in the oven or the autoclave, or how much metal mash you put in compared to where the tools are in the autoclave, you're going to have some colder, you're going to have some hotter spots. So you can add heat. If you have a heater that's on a tool in the autoclave, you can adjust temperature of those tools to meet the temperature of the surrounding tools and get a consistent cure through all the laminates. So there's a number of benefits, or a number of things you can do with heated tooling that aren't necessarily out of autoclave cure, primary structures, demold, debag, off it goes. You can do some pretty general stuff that is really not known to, use a hair dryer to heat up a mold so you can put things down and make them stick. It's little things like that. So there's a number of materials, there's a number of processes that you can use it in, but then there's also the issue of putting it in properly and putting it in safely and putting it in so it's compliant.
Now, we know that, some of these technologies can be difficult to bring to the manufacturing floor. From your experience now, how do we make something like that safe and compliant for the manufacturing floor, for the industry in general?
Right. This is any time that you are going to take electrical energy and you're going to put it into a mold, you're going to put it into anything that what people that realize, and what I even didn't realize at first, and we didn't really come head to head with this subject until we started to go through the UL process to manufacture heaters. You have to do things a certain way to be compliant. In other words, if you got workers on a shop floor and you add a heating system, whether you go out and get nichrome wire or you want to heat up carbon fabric and glue copper buses to it, if you're going to plug into the grid, the electrical grid, and you're going to have an electrical device, and in this case it would be considered a utilization device by OSHA, you're going to have it on the shop floor, you have to follow certain safety requirements. You can't buy a UL approved heater to heat up a carbon autoclave cure tool to do out of autoclave curing. So what do? You have to follow certain procedures that are specified. If someone, and this is where it really fleshes itself out, if you energize a carbon tool, let's say you come up with a system and you put on your own electric heater and you turn it on and it's working, and you developed it in your R&D lab, and someone shocks themselves and gets hurt, or you catch the tool on fire. But if someone gets hurt, OSHA will come in, and so will the local agencies. So you have these things to answer to, and they will ask questions. How was this built? What standards was it built to? And those types of things, before you go down that road, they have to be known ahead of time. So you actually can't do it, but you have to understand what those rules, those codes, the wiring, the cabling, the sizing, the insulation, and those things have to be done ahead of time. And it's really, if you're going to be doing it yourself, that's stuff you have to know. If you're going to be bringing in a heating system from outside, that's something incumbent on the heater supplier to make you aware of all the safety issues that you're going to have to comply to in the workspace and to make it safe. And then you have the whole other technical challenge that you have to make it work. So you have to know, again, one, is it safe? B, how big is your mold? What's your ramp rates? How thick is your mold? What's the laminates you're curing? How much heat flow do you have to have to that? There's all these different calculations that come in that it seems like a lot, but if you think about it, oven manufacturers do this for you, not autoclave manufacturers. Kath doesn't have to worry about is the gas burner going to catch his laminates on fire? Because the autoclave manufacturers have handled that and made that safe and made the wiring and the gas piping safe before they brought it to the plant. So if you're going to be doing self-heated tooling, that same type of safety considerations have to be brought in by the heater supplier, or if you're going to attempt to do it yourself, you're going to have to comply with all of those.
Okay, good. So where do you see the future of heated tooling? What technologies do you see are potentially prevailing out of those that are being developed right now? Lots of R&D out there, of course.
Well, I see carbon tools, autoclave cured carbon tools with embedded heaters in them as being an option. That's a little bit down the road. I see self-heated existing metal tools where heaters are added to the tools. And also in specific areas where they're oven assist. I think that's probably a development that is happening, and it could probably pick up and keep going because some of the companies already have this equipment in place and they're already doing these things, but they're having issues with quality control. They're having issues with temperature gradients kind of all over the map in their parts. So ultimately, the work that is being done, the work that's has been done, the R&D work, I see this going to a self-heated tool, and this piggybacks on the advancements in out-of-autoclave resins. Self-heated tools sitting in one spot, running off temperature process controllers, curing up over 350 degrees Fahrenheit on the shop floor in one place, eliminating the queue getting into the autoclave, eliminating all the other expenses that come with a large autoclave, and doing it in one spot for a lot less cost and a lot less time and a lot less manpower. That's where I see it headed.
Okay. Any other comments from the panel in regards to all that?
I can certainly say I don't know what the end answer is going to be, but having had the need to implement new tools on new programs, I've spent a lot of time, and I know a lot of resources have been spent doing autoclave heat surveys on tools so that you can establish that arrangement of tools on a cart so that you can get an optimal cycle so that it doesn't matter how you stack them or knowing what those parameters are. And all programs that I've gone through have had to go through that process of heat surveying all of their tools and their autoclave loading procedures to ensure that that cure cycle is going to adequately address the different combination of parts that might be included in that mixture. And that's certainly an opportunity down the future to reduce that, that expense.
Right.
Sure.
Okay.
So Alan, we mentioned the your previous work, with the F-35, YF-23, F-18. When you've seen new technologies emerge, how have you approached the implementation of those new technologies onto your programs? Can you elaborate maybe on some of the successes and challenges that you've seen along the way?
Sure. Being, the graybeard or one of the graybeards on the group, I'll kind of talk a little bit about the past to help us understand where the future might be going. I've had the opportunity to participate in the evolution of composites from the days of black aluminum in the 80s to really seeing the potential realized in fully very large integrated structure like the 787, like the A350, come to realization. It's very rewarding to have watched that transition, but it's definitely been an evolutionary process. It's not revolution. It's taken a long time for these technologies to mature to the point where they're implementable. It's been interesting to watch the difference in implementation between the military side as well as the commercial side. The military has always been much more aggressive in their willingness to implement and try new technology, but at the same time, it's very risk adverse. There's a life at stake. There's a person involved, so they're very risk adverse from that perspective when it comes to implementing new technology. So you've really got to have your ducks in order. On the commercial side, you've got to prove yourself to the accountants. If you're not economically viable, I don't care how sexy the technology is, you're not going to get implemented if the accountants don't say, yes, it's a go, because you don't meet the economic threshold for implementation. So it's different to watch the the difference between the types of programs, from my experience. But you see enablers for the implementation of new technology take place in a number of different areas. On the material side, on the fabrication side, on the tooling side, on the NDT side. And they're all a part of enabling the progression of the technology to the point where it's at today. Again, back in the early 80s, the advent of toughened epoxies and bismuth imides really grew the ability to now cover basically the entire OML of a structure with a composite material, graphite reinforced. You had to develop that database for the resin systems, but the reinforcements were already well understood, well characterized. So the implementation that enabled the larger scale implementation of composites to the outside surface of the entire aircraft. You see the design allowables database as being a key to that implementation. I think that's still one of the challenges that we'll see for the 3D preforms. 3D preforms are probably outpacing the ability of the analysis to really design with them. So you're in that design, build, break, which has proven to be a very successful strategy in a lot of cases, but it's because that structural analysis hasn't quite caught up to where the capabilities of the material are. I think you're going to still see some of those challenges with database, with analysis capabilities, as you move into the out-of-autoclave materials, as you move into the nanomaterials, and some of these other 3D printed materials that are coming out. I think there's still a good avenue for implementation through that design, build, break approach, and certainly an earlier implementation available through tooling, where you don't have some of the same barriers to implementation, but it's going to be that evolution through those steps before you see large-scale implementation into flyaway type of product.
Yeah.
I think you see the same thing in the world of tooling, the advances to suddenly be able to build very large-scale, very highly accurate molds and jigs, which was a capability that was inhibited back in the days when you were sweeping things in with templates and plaster, and just the ability to measure it, the metrology advances. Again, I go back to the days where we called them theodolites. But when you started having the ability to measure and accurately validate these very large structures, another huge enabler into building these large integrated products. And again, just another stepping stone in that progress. I would see the same thing with in the fabrication arena. The ability to use laser ply location, away from hand laying up of templates and hard templates for ply location, inhibitors into building large-scale structures. Well, laser ply location has been another enabling technology that has matured to the point where it has really enabled some of these larger structures to be built. Fiber placement is another huge enabling technology. Again, I'm old enough to go back to the days where when fiber placement was first being developed, I worked on it with ATK and Northrop back in the 80s. And it was really a material savings technology. As Keth had mentioned, we're going to take cheap resin and cheap fiber and combine them and get rid of that pre-preg cost, get rid of that expense of the pre-pregging process. Well, toe-preg never really panned out with the quality and the consistency that was required. And we actually ended up with a more expensive material form, which was pre-preg into slip tape. Oh my God. But you've compensated for that, and it's a credit to the fiber placement community that the quality, the consistency, and the laydown rates are really the enabling technologies there that have really propelled that technology and have allowed you to build these large structures without having this out time concern, without having some of the other limitations that you had when you were talking about hand layup. At Rubbercraft, as a small company, the inflatable rubber mandrels that we manufactured, I don't know if people know this, but there's over 2 miles of co-cured hat stiffener on every 787 fuselage structure. So the ability to co-cure hat stiffeners in excess of 40 feet in length, do it repeatedly, do it economically, be able to hit your layup rates, be able to remove from that hollow structure, that's an enabling technology. And to do it in production so you can build 12, 15 aircraft a month. So those are some examples of some of the enabling technology. And that was a progression. We started developing that technology back in 2004, 2005, and working with the Boeing team to baseline that into the 787 structure. You didn't start actually building parts with it until 2010. So there was a long gestation period of actually being able to take that technology from what was a concept and a good idea into actually being implementable
Right.
and being baselined. One of the things that you see also in the world of NDT and inspection techniques to be able to inspect and validate these large structures. If you could inspect them, you can't build them, right? You can't fly them unless you can validate them. So along all these different disciplines, you see these advancements in technology that combined have enabled the progression from black aluminum to large integrated structure. Where does that go? Are we at the limit? Are we past the limit? Have we bitten off more than we can chew? I think a lot of that has yet to be proven in the future, but you're going to see the same path to implementation for these new technologies. It will be evolution. It won't be revolution. There will be incremental steps. There will be advances and successes through tooling and through certain part implementation until you get to that large scale advances, and it's going to be a combination of different things that are going to enable it.
Yeah.
Where I see that future going.
So having worked both with a large OEM and Northrop Grumman, and then also as a vice president of technology, engineering and technology for Rubbercraft, do you have any advice for the small businesses, small companies that are out there on how to get these types of technologies implemented or seen?
Well, it's a good question. I mean, certainly from a small supplier standpoint, it helps to have that niche technology, that enabling technology, that you can find a champion within the OEM community or within a program and work with that champion to advance that technology. That's not always available to you. Most of the small companies, there's a lot of other folks who are capable of doing what they're doing. And we know that there's relentless pressure from the OEMs to reduce the supplier size, the supplier community, not increase it. So as a small supplier, I really think, what we found is that, the three tenets, cost, quality, and schedule, are still golden. Quality has really been one of those attributes that is no longer a differentiator. If you don't have good quality, you're not in the game. So quality has become an assumed characteristic. So you have to have good quality or you're not in aerospace and defense, you're supplying to a different industry. So quality doesn't differentiate you anymore, you're down to cost and schedule. So you really got to be on top of your game in terms of customer satisfaction, in terms of being at the customer's, anticipating what he wants and being able to work very closely with them. It's a challenge for small suppliers because you've got a lot of customers that you're trying to serve, and they all want that. They need that kind of service in order to sustain it. But I think from a small supplier standpoint, you really got to work on your customer service, awareness of the customer, and obviously you got to be good with your technology because there's other people who are good at it too.
I can't agree more with that. Panel, and any other things you want to add?
I'll just jump in here as well. Alan, I really, like you articulated it well, with the small suppliers are really effectively operating in the niche or what I call the innovative space. So a small company can be pretty lean, come up with great ideas, and as long as you keep aligned with small projects, it's a great way to plug in with the OEMs. And the SBIR community is another area where the government will fund small businesses to work with big businesses around an innovation space.
Very good.
Yeah, can I chime in on
Go
that?
right ahead, chime in.
Yeah, can you hear me out there? Yeah, there we go. Yeah, awesome. Alan, that was awesome. No, sorry. Everything he's talking about is great. To chime in a little bit, when I did a lot of R&D for a lot of years, so a lot of you guys might have seen me in the past. I was in the circuit for a while.
Yep.
But we, kind of like you're saying, we worked with a lot of government contracts, a lot of grant money. SCRA worked a lot with. I know they're around here somewhere. The AFRL, Air Force Research Lab, always has stuff going on. DARPA, and we tested out a lot of stuff with fiber placement, ATL, hot drape forming, a lot of more automated solutions to, like you're saying, reduce that cycle time because you have to use that uni tape, you have to use that high mechanical. But even as a tier 2 company, we were able to get out there. You got to be boots on the ground out there, putting in your abstracts and fight for it. But your technology can get used, and it will be accepted by an OEM if you show them, hey, I can save you money. So at the end of the day, that's what it is. It's a business. So a very, very good point. I liked it.
Yeah. Thank you. So Keith, in many of the small companies out there are interested in understanding, how they can get a foot in the door with a Boeing or a Lockheed or a Northrop, a big OEM. From your standpoint, what enhancements could really make a difference in affecting future aerospace platforms?
So Dan, I think we talked a little bit about how small companies work with big companies. Just to re-articulate that, I think one of the spaces is around small projects. It's easier for big companies are always working a small project on the developmental area or in a niche technology. Forums like this are a great place for the small companies and big companies to connect with each other. And then the others, just with the tier 1 or tier 2 integration. The OEMs, there's a lot of bureaucracies associated with it. So if a small company can plug in with a tier 1 supplier, that's a good place to connect. Your second question is, we talked a little bit about the past and the present, but what's the future of composites? What's the future of materials? So I'll try to take that one on and tie a couple of these threads together. So we talked a little bit about heated tooling and the enabler that has to get out of the autoclave. So I think with existing material systems, that's a great area of opportunity that when you're in an autoclave, you're constrained by cycle time, you're constrained by size, and so if you can innovate with tooling, that allows you to make bigger parts or heated tooling in an autoclave to cycle it faster. So that's an arena where even in the next 12 months or 2 years that we should be able to innovate in that space to get the cure time out. The second big play is with additive. Additive manufacturing helps us get out of tooling. So the first step is getting out of autoclaves. Second step is getting out of tools. That if you can 3D print big parts, you can really scale them up, and then you're not dependent on the non-recurring effort around a custom tool. But the key thing that will enable additive manufacturing is you've got to intersect fiber reinforced thermosets and thermoplastics with 3D printed plastics. And so the intersection there is if you can get if you can 3D print with fiber, that'll really change the market. That'll change the environment. That'll change everything. So if you can 3D print thermoplastics with fiber, then you're out of the autoclave and you're out of the tools. Okay, so that allows you to make really customizable parts at large scale, maybe lower rates, but at large scale. Okay. So, the other piece I wanted to hit on was, relative to the material space. I think right now we're in a very much an incremental development space with material systems. That there's a little bit of development going on with fiber, a little bit of development going on with resins. We'll see some development in conductive composites. We'll add things to composites to make them more or less conductive. We'll tweak the resins to have either higher temperature capability or higher toughness capability. And there's always going to be some incremental development in those areas. But the big changes for the industries is going to be in getting out of the autoclave, getting out of the tooling, and really enabling additive and 3D printing.
So how do you foresee these changes, these improvements? How do you see them impacting the aerospace composites and manufacturing environment?
So what will it do to the environment? Well, one of the things you'll see is, I think as the world, you've got desktop 3D printers now that are kind of popping up everywhere. You can go buy them for hobby type things. But as that external infrastructure builds up, you'll see 3D print farms start up at mom and pop shops in Arkansas, where they're not just printing plastic cups and knickknacks, but they're printing structural components or multifunctional structures. That the scalability of that will extend outside of just the big the big shops. And so I think environmentally, it's going to change. And one of the ways to articulate it might be it's going to lower the barrier of entry. So right now, the barrier of entry to composites in aerospace is pretty high. You've got to have a big autoclave. You got to be able to go build, multi-million-dollar INVAR tools. And when you eliminate that $20 million autoclave barrier to entry, and you eliminate that $20 million, $100 million tooling barrier to entry, and you get it into a desktop printer space, it's going to open it, wide open, where there will be a lot of people that will be able to play in the composite manufacturing, composite design arena that didn't have the capital to play in it before.
From your perspective, do you see composites being adopted in greater numbers over time? Or do you think that there'll end up being essentially a plateau once we reach structural requirements are kind of what drive whether or not we can use composites right now. Do you foresee that there'll be a plateau in aerospace composites use based on once we hit that structural requirement? After that, we'll kind of just sit in a holding pattern?
So where's composites headed from maybe a volume perspective on just pick aircraft?
Right.
If you look at modern aircraft right now, it's probably 50% composites, 50% metals, right, from a materials aspect. I think we still have some upward trajectory that composites is still going to take on, as you can unitize more, as you can get the cost out, there will be more composites content in the structure. And there's still some untapped areas, like rockets is still mostly metals. I think there's some space for composites to grow in the launch business, in the satellites business. But from a 50-50, are we going to? I'd say 60-40, 70-30. There's always going to be metals content on aerospace structures. I think what we are going to continue to see is an increase in volume. Right. That the commercial airplane business is millions and millions of pounds a year, and it's still an upward trajectory. That as the Asian market grows, the volume of composites that's going to be built is still increasing. And composites is picking up in other industries outside of aerospace. So I think from a volume perspective, we're still on an upward trajectory. And the more we can unitize and the more we can get cost out, the more that upward trajectory will continue.
Thank you. Panel, anything to add to what Keith had to say here?
Certainly in agreement with Keith's thoughts on where the future is going. I see 3D printing already being utilized in very unique applications today, and that technology is going to continue to grow. So it's exciting.
I very much agree. Well, with that said, I want to thank you guys.